Okay, so welcome again, everybody. We have people from many different um, specialities and locations. We have people from Australia, from the UK, from the United States, from Europe, and people who are in the business of numerical modeling for hydraulic problems. We have people also of government agencies, from consulting firms. So we have a pretty good crowd here. So I will try to be as thorough and comprehensive as I can in my descriptions of the things we have found so far in comparing RiverFlow2D with so-called free models. Well, first, the purpose of this webinar is mainly and above all to provide valuable information for users or potential users to help them select a two-dimensional model. We just want to provide the most accurate and objective information that can help them in this selection. So we have also questions on our own. For instance, can a commercial 2D model be more cost effective for the modeling process? Or we only, it's obvious that free models would be, because they're free, would be more cost effective. So this is questions we were trying to answer. And to that purpose, we have selected three models. Obviously, RiverFlow2D, which is the main model that is developed by Hydronia. And we have picked two leading models that are free, which is the HEC-RAS 2D, developed by the Corps of Engineers, and also SRH-2D, which is developed by the US Bureau of Reclamation in the United States. And we have selected the benchmarks of the United Kingdom that have become a de facto standard to check or verify how models behave in different hydraulic situations. And I will talk about that in more detail. And I want to leave space at the end to your questions and any answer that I may provide to you. To that end, I expect, due to the big crowd we have today, we have already questions already coming in, even though I haven't started the presentation itself. But the thing is that I will answer all the questions that I received today. And those that maybe I don't have enough time to answer during the presentation, I will write them in writing, answer them in writing afterwards, and all of the questions and answers will be posted on our website. By the way, we have a new website, and you're invited to visit that anytime you have available. It will be posted in the same location where you register for the webinar. Now, I have to also first to make a few acknowledgments. First, to our main development partners, Computational Hydraulics Group at the University of Zaragoza, Spain. We have a good research and collaboration agreement with NOAA, North Central River Forecast Center, where we have an ongoing project applying the RiverFlow2D GPU in a large river reach of the Red River of the North. We have also a very close relationship with Aquaveo SMS, which is the main user interface for RiverFlow2D, and it's the main entrance to the RiverFlow2D model. And also, we have an ongoing collaboration agreement with Autodesk, where we have a testing platform, which is the Autodesk Labs created a flooding plugin for InfraWorks 360, and I invite you to visit that site. The project is called Project Boulder. It's in testing, and it will be continuing testing for this year and probably a few months of next year as well. So it's an amazing application we are experimenting with Autodesk. I want to make some clarifications, clarifications. First, well, this is not a disclosure because all of you know that Hydronic has an obvious interest in RiverFlow2D. This is our main model, the model we develop, and the model we distribute and support. So obviously, we do have a genuine interest in this model, but we are going to be as objective as it can be. So all the statements that I'm going to make today, this presentation, are fully supported by numerical tests. And these tests are open and have been made by modelers with demonstrated expertise in using each of the models we are going to be using. So also, we are going to provide to all users who request, for people who request, we can provide all the files used for testing all the models that we are testing today, which are, as I said before, RiverFlow2D, HEC-RAS 2D, and SRH. So the idea is that any of you, anybody, could replicate all that we are going to present today, and that hopefully will ensure that all the statements that we are making are fully supported. Well, first, there are 2 or 3 preconceptions about, well, there are many preconceptions about using 2D models, but I'm going to focus today on maybe 2 of them. One of them is that using commercial models is more expensive. Now, people say, well, let's use this free model because it's free, obviously, because it makes sense. You don't need to spend any money on it. It makes total sense. And also, there are many models that are developed by respected agencies or organizations. So there is the issue of model branding. So if that model is made by this or that organization, then it has a certain prestige, and that requires some it adds some value to it. Now, our point is that more important than who created the model is how good the model is. So that's the bottom line, because you are not, when you are a consultant, you are a modeler, and you're using a model, you are not doing the model with the developer. You are using the model on your own, and you are embedded with the model in creating a solution to a client. So your interest should be to use the best available tool that you can find. And the second point is that the only issue that you should consider in the modeling process is not only the cost of the model itself, because there are many other, and as a matter of fact, more important aspects of the modeling process that add more to the final cost of the whole project than the cost of the software itself. And there are key features in the models that can help you in minimize the costs significantly, even though the model is not free. Now, which models we have selected? Well, first, as I said, RiverFlow2D, HEC-RAS 2D, we'll call it HEC-RAS 2D. It's been called HEC-RAS 5.0. But the main focus here is to understand that we are using the model as a two-dimensional model, even though some of the models may have other capabilities that are not two-dimensional. And then the US Bureau of Reclamation SRH-2D, which is also a two-dimensional model that is free. Now, the questions we are going to try to answer, and hopefully we'll succeed in this, is how do models predict velocities and depth? How do they compare in benchmark tests? How they conserve volume? Are the volume conservation that they report, if they report it, good enough? They're reasonable or not? Then how fast they are? Are the models fast enough? Do they perform, for medium-sized or large-size projects at a reasonable runtimes? Also, how do the models converge to known solutions or to the expected reasonable solution that you may have in particular situations? And finally, the question is a free model always more cost-effective than other options? Well, let me start by giving you a brief introduction to the three models that I'm going to be using, very brief. First, RiverFlow2D, some of you already know. The RiverFlow2D model is a combined hydrologic and hydraulic model, which uses flexible non-structural mesh. It does dry and wet areas with an explicit finite volume numerical engine. It does supercritical and subcritical regimes. It's been extensively validated. It has sediment transport, pollutant transport, mud and debris flow modules. It can do hydraulic structures in 2D. It's fully integrated with SMS, Aquaveo SMS GUI. So you can actually it's the main entrance to the model now. And it's compatible with most of the features that are available in SMS. Very importantly, the model has been parallelized in GPU hardware. So this, in practical terms, it means that it can run up to, according to our test, up to 150 times faster than our own model running in non-parallelized mode. So if you decide to compare the model, the RiverFlow2D, using one core or using an advanced GPU hardware, you can find or expect to find accelerations in the order of 150 times, which has a tremendous impact in practical applications, because it means that a run that could take you in other non-parallelized models, it could take you days, can take you only hours, and runs that maybe take you hours can take you minutes and sometimes seconds. Now, the model is based on triangular elements exclusively, and each element has representations of the velocity components and the depth. And there is an assumption that I'm going to come back to it later, maybe, that the bed elevation is constant on each element. So there is no detail other than the interpolation of the lidar that you may have for the terrain elevations that are used to obtain the bed elevation at each element. Now, the numerical, the basic equations that we use to solve them numerically are the shallow water equations in conservation form. So these are a set of three equations: one equation for the conservation of mass or volume, and two equations for the conservation of momentum. And these equations are used in RiverFlow2D in full conservation or conservative form. Now, the numerical properties that are intrinsic to the RiverFlow2D numerical engine are very important also from the theoretical point of view, but most importantly from the practical point of view. First, RiverFlow2D is accurately, regardless of the flow regime, let's say fruit number, regardless of how high or low are the velocities, how big is the bed gradient, and how are the variations of the flow depths. So in these situations, the model will always be as accurate as it can be a numerical model. Second, the numerical solution is not sensitive to the time step for any given mesh, provided that the Courant condition, the CFL condition, stays below 1. This has implications, as you will see later in the test that I will show today. And what this means is that for a given mesh, you don't need to pay attention to how the model converges because the solution you get has already converged. And that's an assurance that the model, the numerical engine, provides. Third, dozens of numerical tests demonstrate that the model is stable, consistent, and convergent. And I will come to these concepts, which are important to our test today, in any real riverine flow situation, and always. So these are assurances that we can provide about the RiverFlow2D numerical model and are backed up by a large number of numerical tests. This allows to present results such as the one you're seeing here. These are results from the Red River of the North and correspond to about 20, 30 points, measuring points along 420 river miles of the Red River of the North in the United States. And running a simulation of a 50-day hydrograph and comparing the RiverFlow2D results with the field data, we achieve a very good approximation at most locations, except some, few locations that may have some offset here. But that's something that provides trust to a numerical model. And also the model, being a flexible mesh model, can be refined and you get very detailed analysis of the flow fields. And it also has a number of hydraulic components such as culverts, internal rating tables, sources and sinks, bridges in 2D, including pressure flow and overtopping computations in 2D, gates in 2D as well, weirs that are useful tools to model levees and sound walls. And we have recently added an extension to these tools that allow you to have variable crest elevations along the weirs. And also it can do spatially variable roughness. So if you want to model a Manning's N variation with depth, it can do that, but not only globally, but also spatially varied. So you can determine how the Manning's is varying at different locations in your mesh as the depth varies as well. So it's a very cool feature for some applications. Now the model has also a very interesting hydrologic component. It is a full distributed model with rainfall evaporation that can vary in space and time, and also infiltration. And we provide 3 different options for infiltration methods: the Horton method, Greenamt, and the Kerr number method. So all of these can be combined, and they can also be spatially varied. So you can have an area where you want to model the infiltration with the Kerr number, another area you may want to model with Horton method, etc. Now this allows the model to provide a lot of detail depending on what you want in your application. You can model complex hydraulic structures as you want to see here with a large level of certainty in the results. This is a dam break flooding in Mexico. These animations are created by the SMS user interface, where you can export the results to Google Earth in a very simple way. Now, the second model we are testing is HEC-RAS-2D. HEC-RAS-2D, let me first say that it's still in beta form, so all the results we show here may change in the future as the model is released. We have tested the latest beta version. However, we have also used the previous versions, and we didn't find a lot of, actually we didn't find any differences in the results we are going to present in the different previous versions that were released. Now, HEC-RAS-2D is a two-dimensional hydrodynamic flow routing model. It has a 1D, 2D capabilities because it links with the older HEC-RAS 4 point something, a 1D model. You can have independent 2D domains for overbank or channels. It solves the shallow water equations or the diffusion wave equations. To compare apples with apples, I'm concentrating in the test with the shallow water equations because the diffusion wave equations is an approximation that doesn't work for any problem, and since the other models use the full shallow water equations, I'm concentrating on those today. It uses an implicit finite volume solution algorithm. It also uses flexible meshes with a wide variety of elements that you can use. You can use elements with different sides, 6 sides, for example, or squares, also structure meshes if you want. You can mix and match these elements. And it has a very interesting feature whereby you can provide information that is internal to the cells, information about the terrain. So it can capture to some extent the detail of the internal terrain representation to a cell. So I may come back to this later. Now then, SRH-2D is the sedimentation and river hydraulic 2D model of the US Bureau of Reclamation. It uses also an implicit finite volume method with flexible mesh. It does very well subcritical and supercritical flows. It does also sediment transport, and is also integrated with Aquaveo SMS. It seems that hydraulic structures are under development for this particular model. Now, this is a summary of the model capabilities, and I apologize in advance if I'm missing something. Obviously I'm not including all the capabilities of all the models, but I tried to concentrate on those two who are important for most projects related to 2D, purely 2D applications. So, well, first, these two models are free, HEC-RAS-2D and SRH-2D. Actually, what is free of SRH-2D is the model engine, because it actually requires the SMS interface, which is not free. It's a commercial interface. It's not saying that RiverFlow2D uses. The user interface of HEC-RAS-2D is completely included and is totally free. RiverFlow2D is not free. It's a commercial product that uses SMS as well. And the total cost of a license is between $2.5 or $5,000 dollars. Depends. This is for the academic version. The commercial version is about $5,000. So it's a big difference. Now the equations that are solved are similar, although the HEC-RAS-2D do not use the full conservation form of the equations, but they are the full momentum equations used there. The numerical method is in all of them is finite volume, although the RiverFlow2D use explicit method, and the other two use implicit method. This, in theory, you could use larger time step for solving this equation here. They all use flexible mesh. They deal with wetting and drying on steady flows. They report volume conservation, except SRH-2D doesn't seem to report the volume conservation, which is a certain drawback here. And there are some features that are not present in HEC-RAS or SRH-2D, but some of them are under development, I understand. Depth-dependent roughness, hydraulic structures in 2D, sediment transport in 2D, pollutant transport in 2D, modern debris flows. GPU is only available for RiverFlow2D. HEC-RAS is parallelized for CPU processors, not GPUs. SRH-2D is not parallelized. And RiverFlow2D is provided commercially, and that includes free technical support directly by the company Hydronia. And these models are supported internally on their agencies, but are not supported by their developers outside of the agencies, but by third parties sometimes. Now, the numerical model requirements that are most commonly sought after in models are listed in this table. First, the convergence, which is an intuitive concept where the numerical solution needs to converge to the exact solution as the time step and the mesh, the size of the mesh, tends to 0. So the concept here is that as the mesh and the time step is reduced, the solution needs to converge to a solution, hopefully to the exact solution. Now, this is an essential property, obviously, because if you increase or reduce supposedly the error by decreasing time step, you don't converge, then the model is not converging. Now, there are partial conversions. For example, you can only change the mesh, but the mesh often also drives a reduction in time step. But you go also for a single mesh, reduce the time step, and that should, desirably would also converge to a solution. Maybe not the exact solution, but for some solution. Then you have some other concept we have analyzed, like consistency, stability, and conditional stability. I'm not getting into the details of this, but I just want to point out that the unconditional stability means that the numerical solution is bounded for all time step or current number. That's rarely a model can be unconditional stable. Most models are conditionally stable. The ones we are dealing with today are conditionally stable. They have a condition by which, if you respect that condition, the model will be stable. In the case of the RiverFlow2D, that condition means that the current number needs to be smaller than 1. And for HEC-RAS and SRH-2D, that condition is a little more flexible, and you can use larger, in theory, larger time steps. Now, which test are we using? As I said, we are using the UK benchmarks. The objectives of this test are to, they were developed by the UK Ministry of Environment to provide an evidence base to ensure that 2D flood inundation modeling packages, so the software, the models themselves, used for flood risk management in the UK, and also by consultants, are capable of predicting the main variables, which are velocities and depth, which flood risk management decisions are based on. So they provide a data set against which the packages can be evaluated by their developers. Now, obviously, they can be evaluated by developers, but the data set can be used by anybody so that anybody with an interest can check if how the models behave or how they compare with other models. Now, there are 8 data sets. Due to time constraints, I'm only focusing on 2 data sets today, which are the test 5 and 6B. Now, what are we focusing on? We are comparing velocities and depth. we want to know how the model predicts flow wave propagation. That's a very important question to address. How do models conserve volume? As an example, for a 50,000 acre-feet dam break, so it's roughly 68 millions of cubic meters, a 0.1%, which is, could be considered a small errors, translate in a 44 acre-feet volume error. So what it could appear as a small error, it could translate into a not small error in volume, and that error in volume obviously translates into different depth and different velocities. The other questions we try to address is, what about the convergence of the model? How do the model converge when reducing particularly the time step? Because the requirement of the UK test is that you use a specific size of the mesh. So they have specifications for how many elements you should use for any given application. What is the model sensitivity to time step or the current condition, and how fast are the models? So we tried on each of these two tests to answer these questions. Now, the first test is test 5. The objective of this test is to evaluate the model capability to simulate major flood inundation, so it's a big event, and to predict the flooding out of a dam failure, peak velocities, peak water levels, travel times, etc. Now, the test is designed to simulate the flood wave propagation on the real terrain in a river valley out of a dam break occurring here upstream. So this is the river valley. You have a confluence downstream. So this is the inflow location where the hydrograph is specified ideally with this curve here. And then there are locations, if you look at here, 1, 2, 3, 4, 5, 6, 7. These are 7 points that are required by the UK benchmarks to compare. So these are the observation points where we are going to extract results. I'm going to present a few of them today, but what the points I'm checking correspond to upstream, medium size, and downstream. And this is the profile along the line that you see here, this green line here. So it's quite steep on the upper part and quite flat on the lower side. So it opens a way to check a number of features on numerical models. Now, these are the tests for results for 0.5, 6, and 7. Let me go back here so you understand where are the points. 5 is downstream, 6 is upstream, and 7 is in the middle. So I wanted to cover this, different points at different areas, because these are not that different here. They're very close. Okay, so I'm comparing here RiverFlow2D results, HEC-RAS with 2 different time steps. I will explain why we use different time steps for HEC-RAS. And these are the results for SRH-2D. So these are velocities and these are water elevations. So at first sight, it would appear that the 3 models behave very similarly. But if you look closely, you will start to look at differences. Well, first here, the RiverFlow2D and SRH-2D are not that far. I would suggest they're close for this particular case. This is a velocity here too. HEC-RAS, the first run we did was with 2 seconds, which is this point here. That's a big difference, very big difference in the frontal wave arrival and also the magnitude of the velocities. Now, by increasing the time step to 10, the results look much more similar to the ones we get. They're not so close, but they are closer to the ones we get with RiverFlow2D or SRH-2D. And the same behavior applies to water level. There are some other points where the differences are not that big. Actually, they are quite similar here. Here they are in between, I would suggest. It depends on the time step you pick. And there are some other points where there are also big differences here. Now, in regards to volume conservation, as I said, SRH-2D does not report on volume conservation. So I'm only presenting HEC-RAS and RiverFlow2D. Now, HEC-RAS volume conservation seems to depend on the time step. So for small time step, the volume conservation is 0.08%. This is 0.08%. And it goes down and then up again, depending on the time step. Now, these values may be small. Okay, it's not that big. What I think is that they are unusually high for a finite volume method. Typically, the finite volume method, one of the characteristics is that they can conserve very accurately the mass at the element level. And you typically expect much lower values of the volume conservation. But that's what it is. Now, the volume conservation of RiverFlow2D is 10 to the minus 14%. So you cannot even see it here. Now, this value may appear unusually low, and maybe if you compare with other models, but this is the value that you should always expect and you will always get from RiverFlow2D model for virtually any application and any project, regardless of the flow regime, the time step, the mesh size, etc. Now, let's look at the time sensitivity, how the time step affects the model. This is RiverFlow2D results for two. In RiverFlow2D, you don't give the time step. The time step is automatically computed. You only provided the current number. So we selected two values just to check if it was any change. Current number 1, current number 0.5. Typically 0.1 is the value that is recommended, but sometimes you may want to use a lower value. But there is virtually no difference in the model results at any point with respect to the time step. Remember that the mesh is the same in all cases. SRH-2D, which is also a finite volume model, although it does not report on the volume conservation, I would suggest that the volume conservation of this model is comparable with RiverFlow2D, because when you look at the results here, at least there is no variation with time step. So the model is unsensitive to the time step or current number you use. Now, the issue with RAS2D is different because it's highly dependent, at least for this particular case, to the time step. So you can see big differences here in the frontal wave arrival of up to an hour. So depending on the time step you pick, you may get a difference in almost 1 hour of the frontal wave arrival in this particular location. Now the water elevation seems to be very insensitive in some points. It's more sensitive in all other points. Also checking runtimes. So these are RiverFlow2D run in different platforms without parallelization, only one CPU, with 8-core CPU, with a medium priced GPU card, with a better GPU card, and then HEC-RAS with 2 seconds, which is the lowest time step we used, with 15 seconds, which was the largest time step we used, and SRH-2D. So the difference here is from the fastest RiverFlow2D, we get HEC-RAS with 2-second time step, 57 times slower, 37 times slower than RiverFlow2D with 15 seconds, and SRH-2D 99 times slower. Now let's go to the second test. This test is performed in a prismatic channel, but it's a dam break test with the West design in Europe to check the ability of the models to reflect realistic dam break complex flows coming from a dam break, and including situations where you can have hydraulic jumps, obstacles, etc. And you have here the locations of the measuring points and also the locations where the models are compared. Now, again here, you can see that the models in some cases are provide similar results, particularly RiverFlow2D and SRH-2D. HEC-RAS still behave a little weird in some situations that can vary significantly with the time step. And I will talk about that more in a minute. Now, the volume conservation again in HEC-RAS has these values, and it vary a bit with the time step. And RiverFlow2D volume conservation is still very low. Now, runtimes in this case, you get here depending on which time step you use. This is the maximum time step we could use in HEC-RAS2D. It's 11 times slower or 41 times slower for a smaller time step. Remember, we're using the same mesh, or roughly the same mesh in all cases. And SRH-2D is 217 times slower than the fastest RiverFlow2D, which is this one here. Now, time step sensitivity, again, for RAS2D is much better now than in the other case. However, there are some, if you look closely, you will see in the peak water elevations at some points, difference that may not be at first sight very big, but when you look at closely, there are differences in 28% in the depth predicted at some points. So that can be in actual projects problematic. Now, the time step sensitivity of RiverFlow2D again is 0, and so we didn't do the time sensitivity. Actually, we did it, and it was as good as RiverFlow2D for SRH-2D. It's just I didn't include it in the presentation. Okay, so we found these issues in HEC-RAS2D, which we didn't expect it actually. The velocities and depth are sensitive to time step for the test that we ran. Okay, I need to say that we ran only a few tests, actually 4 of them, but the ones that I'm presenting here, 4 in the test we did, the velocities and depth are sensitive to time step. But something that is a little concerning is that the solution deteriorates when you reduce the time step. So it would appear that the model is not, for some cases, it's not converging when you reduce time step. On the contrary, it improves when you increase time step, which is a little weird. Now, the differences in velocities and depth by changing time step are high in some locations. Now, we communicated to the core these findings in advance, and there are some answers to it. Now, what they indicated is that the solution should converge when reducing simultaneously the mesh and time step. So it would appear that if you are able to reduce simultaneously the time step and also the mesh, you should achieve convergence. We couldn't do that those tests because these answers came later yesterday. And it would appear that the reason for that is that the current RAS uses a non-conservative form of the momentum equation, and that makes it accurate for a limited range of current numbers. So it means that in some situations where you have very fast flows, like the advective terms are very important, the model is not able to converge as it should, or comparable to with other finite volume models. Now, the Corps of Engineers is working on alternative methods to solve this issue, as they indicated. So I wanted to express that because results were really concerning to us, and we wanted to make sure that we got them right. Now, in summary, for each model, first, for HEC-RAS, the results are very sensitive to time step for the test we did. The volume errors are high, in our opinion, for a finite volume model. The volume errors also depend on time step, which is a little unusual. Reducing time step does not improve solution. Again, we didn't test the changing in mesh. The problem with changing in mesh is that the mesh size we use is the one that the UK requires. We cannot, I mean, if we would reduce the mesh for one model and not for the other, we would be comparing not apples with apples, but something else. So anyway, we didn't test that option. So the accuracy seems to be problem dependent. There are some problems and some points where the results are much better than others, and things like that. Now, the main issue here is which time step would you use for this model in a real application? So I would expect from a modeler point of view that you would try to get smaller time step to get a better solution. Now, if you had data to compare with, that would be fine because you can tune in the model. But if you don't have the data for proposed conditions or design conditions, you have no way to fix the time step in a objective way. So that's a question we have. Now, the SRH-2D summary results are comparable in accuracy with RiverFlow2D. It does not report volume conservation, and it's the slowest by far of the model tested. So it's in my opinion, it's a model that provides good accuracy, but be prepared to wait for the solutions, because even though in these cases the mesh are relatively small, if you intend to use this model for high resolution hydrodynamics or long reaches, you should expect very, very long computer times. Now, in RiverFlow2D, the volume conservation is virtually zero for all cases. It's not sensitive to the Courant condition, and it's between 11 and 57 times faster HEC-RAS2D in the two tests that we did, and between 99 and 217 times faster than SRH-2D in the same tests. Now, coming back to the issue that I first mentioned about the cost of the model and the fact that the model is free or not. We did some survey, informal survey, and maybe not too well done. We have done this over the years, so be kind to what I'm going to present here, because the actual numbers doesn't matter too much, and may be wrong in some cases, but the point, I think, is right. We identified, based on users' experience, what are the factors affecting the cost of the more important factors affecting the cost of modeling tasks, like model package cost, computer and software, software, other software like GIS software and things like that. GIS pre-processing time, model conceptualization, model setup, tweaking model to make it work, whatever it is, modeling waiting for runs, result analysis, GIS processing, and technical support is a different thing. So this survey indicates something like this, that the two most important factors affecting the cost of a modeling project are the tweaking the model to make it work and monitoring and waiting for runs. So there are other important factors as well, but it turns out that the software package cost is the one that is less important in many projects. Obviously, if your project is, if you're doing a very small project, and you consider you don't factor out the cost of the model in different projects, that will be a big cost. But in general, the cost of the software is not the most important. It actually is the least important factor in a modeling. But the tweaking the model to make it work, if you spend a lot of time adjusting the model here and there for the different runs you make, or if you have to be waiting long hours or days to get the results and be able to analyze results, these are the critical factors that you need to address in a modeling task, which seem to indicate that the actual fact that the model is free wouldn't be the guidance to select a model, because that's not the most important factor in most cases. So, to wrap up, my final comments are as follows. I think that comparing models with benchmark tests offer valuable information that can be used by anybody to make us a reasonable decision whether to use a model of this model A or B. The questions that you should ask yourself, I think, is, can you trust the model that you have selected? Because performance is secondary to accuracy. Performance is important, but accuracy should go first. So you should compare performance after you compare accuracy. Now, can you trust your model? Can you trust your model that you are going to do in a new application? Believe me that this touches on very closely to our development history. We have done mistakes in the past that we have corrected, and this because every model has bugs, and the fact that you are able to correct and improve the models to the level that we think we have reached nowadays is what embeds the trust in the long run. Now, clients want the best results and the projects finished on time and within budget. They probably don't care if you don't pay anything or pay a lot for your software. What is important is that the results are correct and are good, and the project is finished on time and within budget. And in this regard, the model cost becomes a small fraction for most modeling projects. As I said, the model accuracy and speed are critical to reduce the time you spend doing the model. And technical support makes a big difference. Now, you may have a free model. Maybe you're very happy because you don't pay anything for software. Oh, I'm very, very happy. But then in the middle of a project, you find a bug. One of these bugs in your model. Typically, with a free model, you don't have a way to get a response or a solution very quickly. It's not always the case. There are cases where you can get a quick solution, but in most cases, you get the quick solution from a commercial model, because that's the promise of a commercial model, that you will get the technical support you need during your project development. Now, I invite you to look at the big picture here. Now, evaluate the overall modeling process cost and not only software cost, because you may be misled to select the model that will end up not being the most economical one, which could be that the free model may be the more expensive solution in some situations. Now, all things considered, models such as RiverFlow2D, we are convinced that can be the most affordable and cost-effective option for 2D modeling projects. Obviously, as I said at the beginning, Hydronia has an interest in RiverFlow2D, but we are convinced that what we have presented today here can be reproduced by any of you who would be interested in doing that. And again, we are open to provide to any of you the files and more detailed results of what we have obtained here today. Now, to close and before starting to answer some of the questions that have been coming, I want to invite you to visit our new website that has been totally redesigned, and it's pretty nice. I think it's more clear. You will find better information there to help you understand things we do and how we can help you in some of the things we do. Okay, so let me start by asking some questions here. So, okay. Okay, I have a question here. What solution equation method did you use in your HEC-RAS runs? Diffusion wave or full momentum? It's full momentum. We use full momentum in all our runs with HEC-RAS. We haven't used the RAS. By the way, let me indicate that the runs, HEC-RAS runs, SRH runs, and RiverFlow2D runs, Hydronia hired a consultant to do this for us. We didn't do these runs. Any of the runs you see here, we just verified them, but the runs were performed by a consultant, independent consultant that did the runs for us. What is the time step for RiverFlow2D in the runtime comparison? Oh, much slower than the other models. RiverFlow2D time steps are very small. I don't recall exactly, but they are smaller. Close this here. How many CPUs were used in the HEC-RAS? 8. HEC-RAS runs had 8 CPUs used in their runs with a Xeon processor.